Hey guys, welcome to another video. In this video, we're going to be finalizing the AB material for Unit 8 for 8.11 and 8.12, which is Washer's method to find volume of revolving solids. So if you remember from the previous lessons in disk method, we were usually rotating solids around the x-axis, around the y-axis, and we were finding the volume using the integration of pi radius function to the power of 2. So in this situation, we're basically doing the same exact thing, but the only difference over here is that we're finding the volume of the solid in which this solid is an intersection between two functions. So if you look at number 1, for example, they told me to find the volume if the region is enclosed by y is equal to square root of x and y is equal to x squared is rotated around the x-axis. So if we zoom in over here, we can see that the volume of this solid, when it's being rotated around the x-axis, it's going to create this shape over here. So you can visualize this shape. So if it's going to turn around, it will basically give you this shape that I had a snapshot over here. So you could see like there's an opening in the middle. It's empty from the middle. So if you want to look at the cross section, the cross section is going to be something like this. That's going to be your cross section over here, where you have a big area. You have like the large radius, and then you have a small radius. So this is how you can visualize it. So what is the large radius function and what is the small radius function? So if you look at the function back over here, the large radius function is obviously the one that is on the outside, which is this side over here, right? And that belongs to y is equal to the square root of x. And if you look at the inside function is going to be this side over here, and this belongs to y is equal to x squared. So this brings us to a very, very, very simple formula, which is the volume of such solid over here. Let me just highlight it in purple as well. The volume of such solid over here around the x-axis is given by the formula V equals the bounds over here are basically 0 to 1. Pi, what's the big radius? It's going to be square root of x squared minus the area of the small radius function, which is x squared. So you can take pi outside if you want as a common factor. So pi between 0 and 1, square root of x to the power of 2 minus x to the power of 2 to the power of 2 dx. So all in all, in general, how does this formula look like? It looks like this. So pi r of x to the power of 2 minus pi lowercase r of x to the power of 2 dx. Of course, you can like take into account if it's going to be dy or according to the y-axis or anything like that. So let's just repeat one more time. This formula is used whenever you want to find the volume of a solid rotating around a certain axis, and this solid has an empty it has like an empty hole inside of the solid itself, where its cross-section looks like a donut over here. So obviously the volume is going to be the volume of the bigger radius function minus the volume of the smaller radius function. So you can get anything in between them. All right. Now, in the second question, we're basically doing the same exact thing, but over here, instead of we're rotating around the x-axis, we're rotating it around the y-axis. So over here, since we're rotating this solid around the y-axis, basically it's going to rotate over here. So we're going to get something that looks something like this, and then it's going to create this shape over here. So you could see over here that the big function, since this is rotating around the y-axis, the big radius function, we're going to do a projection over here. Where does it touch first? It touches this function, which is y equals x squared plus 1. But wait, you need to remember, since we're rotating it around the y-axis, it means that my volume, no matter where it will be, it's going to end with dy. So everything inside of the integration needs to be in function of y. So basically, I need to rearrange this function over here. So x squared is equal to y minus 1, which gives me x is plus or minus the square root of y minus 1. And since we always take the positive side of it, so x is equal to the square root of y minus 1. That's what it touches first. And then the small radius function is over here. The small radius function is given by y is equal to 2x plus 1, which means that x is equal to y minus 1 divided by 2. So the only thing left for me to find is basically the bounds, and the bounds are pretty obvious. The bounds, the first one is 1 and the last one is 5. So this gives me that the volume of the solid is going to be 1 to 5. Let's put pi outside. Let's put pi outside and just take it as a common factor right away. So inside of the integration, I just need to write r of x to the power of 2, capital R, minus lowercase r of x to the power of 2. In this case, these r of x functions, they represent what? They represent the square root of y minus 1, and they represent y minus 1 over 2. So the first one is going to be square root of y, which is the big one, y minus 1 to the power of 2 minus this one, y minus 1 over 2, all of it to the power of 2 dy. Note that I do not solve the answers for this integration because you're expected to the numerical values of these integrations, because you need to use a graphing calculator to do that. So, or you can use Desmos and just plug it in and you would get the answer immediately. So yeah, this is how to use washer method on rotating the x-axis and around the y-axis. Now we're going to do two more exercises where we're rotating around a certain axis that is not necessarily a y-axis or x-axis. So in this question, they said, find the volume if the region enclosed by y is equal to the square root of x, which is this one, and y is equal to x squared, which is this one, is rotated around the line y is equal to 2. So we got this line over here, which is my rotating axis. So if I'm going to rotate around it, it's going to end up with something like this. So this portion over here, when it's going to be rotated to the other side, it's going to look like this. So if you want to imagine it, it's going to give me this shape. Okay, if it makes sense. Of course, over here, it looks like a jar, right? So it is empty inside, as we know. So literally the same exact thing. Big radius minus the small radius. But the only difference over here is that in order for you to calculate the radius, we need to calculate it from the center of the circle, which is over here, right? So if the center of the circle is at y is equal to 2, this distance is going to be the small radius, and this distance is going to be the big radius. Now, what is the small radius and what is the big radius? The big radius, we touch y is equal to 2 first. So we're going to start with 2 minus, and then it goes down and touches x squared. So it's going to be 2 minus x squared. And the small radius, it touches y is equal to 2 first, and then it's going to touch square root of x second. So that's going to be my small radius. So the volume is going to be, where are my bounds? Let's put pi first. Where are my bounds? Since it's y value, so projection down on the x, so we basically need to see the bounds on the x-axis. So it's going to be 0 to 1. Okay, so 0 to 1, r of x, the big one, is going to be 2 minus x squared, all of it to the power of 2, minus, and then 2 minus square root of x, all of it to the power of 2 dx. So far, so good. All right, So just remember, the reason why I know that the integration must end with dx is because my projection of the radius was perpendicular to the x-axis. So always remember, whenever the projection is perpendicular to the x-axis, I need to use dx. Whenever the projection is perpendicular to the y-axis, then I need to use dy. Okay? Now, second question. Find the volume if the region enclosed by x squared, y is equal to x squared plus 1 and y is equal to 2x plus 1 is rotated about the line x is equal to -1. So this is the solid that I'm looking for over here, and I'm rotating it around x is equal to -1. So all in all, I think that it's gonna look like this. Let's see. So over here, 1, 2, 3, 1, 2, 3 here, and 1. So yeah, like this when it's gonna rotate. So just remember that it's gonna rotate around this axis. So this is basically how it's gonna look like. So as well, it's gonna look like a jar. Now over here, the big radius, remember, it's gonna, first of all, let's say that the big radius is gonna touch this function over here, and then it's gonna touch x is equal to -1. So the big radius is gonna be from here to here. And then the small radius is gonna touch from here to here. Now you notice that the projection over here is perpendicular to the y-axis. That means my integration should be with dy, which means that I have to transition every single function I have from y in terms of x into x in terms of y. So then this function is going to be x squared equals y minus 1, which gives me x is equal to the square root of y minus 1. And this one is going to be x equals y minus 1 divided by 2. And the bounds are obviously on the y-axis, which are 1 to 5. I have everything I need right now. So I'm going to start by answering the question and say that the volume is going to be pi. Integration from where to where? 1 to 5. Big radius. The big radius is going to be from this, so the bottom arrow over here, which is going to be square root of y minus 1. And then it goes to the left until it reaches x is equal to -1. So minus 1, all of it to the power of 2, minus. And then the small radius is going to be, it's touching the straight line first. So it's going to be y minus 1 over 2, minus 1, all of it to the power of 2 dy. So just let's simplify it a little bit more. 1 to 5. Square root of y minus 1 plus 1 to the power of 2 minus y minus 1 over 2 plus 1 to the power of 2 dy. So this is it for Washer's method, guys, and this marks the end of the AB material for Unit 8. I hope you guys understood. If you have any questions, please leave it in the comments, and please make sure to watch the other videos of Unit 8. It will help you a lot. Thank you so much for watching, and bye-bye.